So we will develop a better version in the future, a bit more complex. But for the moment, the quick optimization that we can do it now is to actually not check for the creatures that you already checked. Because let's say that this circle and this circle collide. Now they have checked to each other, but let me actually make a drawing. So let's say that I have this circle, and this circle checks if it collides with the other one, and it's true, but then also the other check if it collides with the previous one, and this is actually redundant because this we already know that they collide. So in order to avoid the comparison with the one we already checked, we actually just have to set j equal to I plus 1. And then this checking here, this if statement is also useless then. And in this way, our algorithm will be a lot faster. As you can see, I jumped back to 120 frames per second. Okay, so now we have this nice collision checking algorithm. Oh, and I'm still missing something, because as you can see, if two creatures collide, actually only one of them becomes white. And this we have to set it actually in the collide function from the creature class, because we have to say this gets white, but also the other gets white. So other color equal white, and otherwise other dot color equal red. So okay, now let's see. Oh, somehow it's not working. Let's see what is the problem now, because only one is actually getting white if two particles collide. So okay, actually I reasoned a bit about it, and actually it's correct that only one becomes red, because if you think, we are checking for example the first with the second, and then become both white, right? But then the second checks with the third, and doesn't check anymore with the first one, because we say that j is equal to I plus 1, so it just checks with the next one, and maybe it doesn't collide with this one, so it actually becomes back red, and this also stays red. Okay, so it's actually correct, but this will have no effect in our code later. If we say, for example, this math.random and this math.random, and we set it here, that we can see, and we actually comment this or delete this, then we can see it that in the same moment in which they meet, they actually both become a random color. So this is applied to both of our particles. Alright. So, okay, I went to 20 particles, but let's actually go back to 100. Let's delete this if statement. This I added while I was debugging. Okay, and for example here where we post the number of creatures we created, we can add a string like number of creatures, double points, like that. Okay, so now let's actually make these creatures bounce against each other, Before doing this, let's actually write a new function let's a new property of the creature class. Let's call this acceleration. So this will be the acceleration of our creature. So our acceleration, and this will be a new vector. We will start with the vector of zeros. And then in the update function of the creature class, we will say this dot velocity dot add this acceleration, and then at the end of the update function, we will say this dot acceleration dot mult by 0, so the acceleration will be reset. Let's actually check the borders at the beginning of the update function. So okay, nothing actually is changed because the acceleration is actually never, so our acceleration is never modified actually. Let's use, for example, the acceleration on the borders thing. So instead of saying this position x minus equal to a bit of offset and then the velocity and so on, let's actually do like this. Let's create a new vector, so bar, and this will be our temporary acceleration. So this will be a new vector of zeros. And then let's say if this is at the border, so if we are at the border with the x, then let's say that h.x it's equal to actually, and we should get now kind of the sign of our position, so of this position dot x. There is no sign function inside JavaScript by default, so I will actually I just got one from the internet. Let me get it. So this is a function that I just got with a little bit of googling. And yes, now we have the sign of our position with this sign function. So you can actually directly copy it from the file, or you can stop the video now and just write it down. Otherwise, just copy it from the file attached to this video. And okay, so this is a sign function that returns us the sign of a number, and in this case it will give us the sign of the position, because if it's less than the Windows ratio, it means that we are on the negative axis. If it's positive, it means that we are on the positive one, and we actually have to multiply this by -1 because we actually want the opposite of our sign. Because when we are on the right side, we actually want to bounce back. So we have to get the opposite sign of the axis in which we are. If we are in the positive x, we want to get in the negative direction. And then we will do the same thing for the y. Let's actually copy that and say hy. Let's actually call it like bounce. So bounce x, bounce y will be this position y multiplied by -1, and then we will say this dot apply force. This is directly from the Nature of Code book. It's how Daniel Schiffman kind of applies this force. He always uses this apply force function, which we will create in a second, and then we apply the bounce force. So now what we miss is this apply force function. Let's go and create it just in the beginning. So let me get this separator, copy it, and create this function. So this apply force equal to function. This will be our force. And then basically the thing will be that our acceleration, so let's create actually a temporary force. So var force equal force dot divided by our mass, which we actually don't have yet, and then our acceleration will be we add this force to our acceleration. So that's it. Oh, and this will be a div new, because we don't want to modify the original vector actually. So yeah, this will be a div new, or actually don't, or maybe we don't care. We can also modify the original vector, so we can just say force div mass, and then we add the force to the acceleration. So now we need the mass. So the mass we can create it here. So this dot mass in the creature class, and let's actually link the mass to the size of our creature, which makes sense, right? So the biggest is the creature, the bigger mass it will have. So let's just use this as our random number, so this dot mass, and the mass is not defined, of course, because this is actually this dot mass. And then there is another error, acceleration is not defined, sure, because this is this dot acceleration. Okay, so what is going on now? It seems there is something crazy. Ah, yeah, because we are dividing, but actually we should be multiplying, because this is a number between 0 and 1. Okay, but it's still kind of going crazy. So let's see what is the problem. Okay, I think that this the problem here is simply that this is quite of a super big number. So let's actually reduce it. So let's say bounds, mult, new, and then let's multiply for a very small number. So let's see. Okay, alright, yeah, now it's working. So as you can see, when they arrive at the borders, they kind of get bounced back, but in a way for which they don't just bounce on it. It looks like there is a kind of a force which pushes them back on the center. So let's see. Yeah, exactly. As you can see, the fastest one will bounce back later, because they kind of more forced that to push against the boundaries. We can actually also add an offset to the borders to see this kind of, we can see this contrary force taking effect before the particles are exactly on the borders. So let's write border offset, and let's say 0.05 for example. And then let's add it to the window ratio. This is the minus part. So minus window ratio minus border offset. No, plus border offset in this case. So let's see, this is where they go on the left. Okay, and then on the right, let's also add a minus border offset. Then for the epsilon, minus 1 plus border offset, and plus 1 minus border offset. Okay, so now this border offset will be, yes, exactly. Now it seems like that they are kind of accelerating. When they hit the border, it seems that they kind of accelerate, which is kind of strange, because the acceleration at the end of the update, it's always set back to 0. I think we should actually just clamp the velocity in a way that it never exceeds a certain amount. So to do that, let's actually go in our vector class. Let's actually go in our vector class and create a new function called clamp. So this dot clamp equal function, and we need a minimum and a maximum to clamp our function. So this is a bit like the clip function inside max, the clip object inside max. And this will go like this. So this dot x equal math dot min. So the minimum value between math dot max and our this dot x. So the maximum between x and the minimum, and then a minimum between the result of this operation and the maximum that we set as an argument. Alright, so let's just copy this for the epsilon and the zeta also. So this dot epsilon, this dot z, okay, and then let's clamp the velocity before, after we add it. Actually, it's also, let's actually clamp it before we add it. So this dot velocity dot clamp, and then let's set let's actually use our max velocity. So this dot max speed, so minus, because it will be our minor value, and then the maximum value will be the positive. So alright, and now we clamped it in between the minimum and the maximum, so it will never go above these numbers, our minimum speed or our maximum speed. So if we change max speed now here to be a bit bigger, then I will surely accelerate. But it was actually good as it was before. So now you can see that when the particles approach the borders, they actually kind of get pushed back in a smooth way. Okay. So let's actually make them bounce against each other. So let's go here in the collide function, and let's say, okay, if they actually collide, then let's say this dot apply force. So we want to apply as a force the particle, the vector that goes from the other particle to these particles. So let's say if we have these two particles or creatures, we want to use, this is our creature that is testing against the other, and we want to apply as a force the vector that goes from the other to our current creature, so that she will kind of be repulsed in the other direction. Sorry for the super bad drawing, but I hope it kind of gives the idea. So in order to get this direction, let's create a new variable and say var dir, and this will be, so this position dot sub new, so let's return a new vector, other dot position. And okay, and then let's say this apply force dir, and to the other, so the other particle will apply the opposite force, so other apply force dir dot mult new, so we return a new vector -1. Okay, so let's see, and okay, as you can see, they are kind of repelling to each other. So it's working. It's crazy to say, but it's working. So I save again. Let's actually make small kind of static changes. As you can see, that the frame rate kind of dropped a lot at the moment, even because I'm recording, but also because creating all these vectors kind of occupy our processor. So let's do a little change here. Let's make them a bit smaller. Let's actually create a couple of variables. So var max size equals 0.08, maybe let's say equal 0.05, and then min size equals 0.02, and let's replace these variables here. So max size plus min size, and alright, so now they're a bit smaller. Let's make maybe the border force a bit stronger, so 0.03. Okay, I think I will make the border of the frame circle a bit bigger. That's too much. We can also reduce the number of these segments by calling the function before drawing. We can call the function mySketch.shape slice and then something like 10. So the frame circles will have no, actually it will draw all these circles with less vertices. So this is what we get. So which is kind of working. The particles are repelled against each other and they will kind of bounce against the borders. There is a minor improvement that we can do here. So instead of you creating then another vector to get the distance squared, we can actually just create a function in our vector class to get the magnitude of this direction vector, which will be then like the distance between these 2 points in space. So let's create a new function in our vector class. So this dot mag, which will actually be very similar to the distance function, except that it will work only with our vector. So this will be something like this: return math.square root of this dot x multiplied by this dot x plus this dot epsilon multiplied by this dot epsilon plus this dot zeta multiplied by this dot zeta. And let's actually also create the version squared, so without the square root, so mag squared, and then let's say return the same thing without the square root. And then we can say, instead of using distance square, so we can actually delete this, we can just say dir.mag squared here. This is a function, and it should have the same effect, but we will spare to create a new vector just to get the distance. Okay, so this is it for the collision detection and bouncing off of these particles. And in the next one we will see some more stuff. So we can maybe start to think about some behaviors for our creatures, and maybe they will start to maybe shrink or get bigger according to maybe they're eating other creatures and this kind of stuff. So we can really go crazy, and now the fun can really start. Okay, so guys, I hope this was useful or interesting, and I hope to see you in the next video. If you like this video, you can support me on my Patreon. Anyway, to download the patch for free, or to download a lot of other patches if you decide to support me. Okay, so see you in the next video. Ciao.